Hi, thanks for joining me today. I've got a really interesting problem. Imagine we have an infinite grid, so kind of like an infinite chessboard. And what we want to do is place the positive integers into each small cell in this infinite chessboard. And so the rules are that if you have the same positive integer in two different cells, then those two cells must be a distance of strictly bigger than that integer apart. So, for example, in this setup here, I've got the number 1 here, and if we look, I also have the number 1 here, but this is fine because they have distance more than 1 apart. And how I define distance is kind of the shortest path which from square to square, and you're allowed to have diagonals. So, for example, here I could go, that would be 1, and that would be 2. So the distance between these two squares is 2. And 2 is strictly bigger than 1, so this is fine. If we look at, say, 2 and 2 here, the distance between these is 1, 2, 3. And so 2 is, so the distance is 3, and that is bigger than 2, so that's fine. Similarly, the 3's here, they have distance 4 apart, 1, 2, 3, 4, so that's fine. And if I look at these 5's, these have distance 1, 2, 3, 4, 5. Wait, I messed it up. 1, 2, 3, 4, 5, 6. Sorry, yeah. So they have distance 6 apart, and 6 is bigger than 5, so this is also allowed as well. And you can see that there are no other repeats in this setup. So of course here I haven't filled in the whole chessboard, I've just filled in what, a 3 by 7 rectangle part of it. We want to know, is it possible to fill in the whole infinite chessboard with positive integers such that it has this property that any two cells which have the same number in, those two cells have distance strictly bigger than that number apart. Okay, so if you want to have a go at this problem, pause the video now and give it a go for yourself, and I'm going to dive straight into a solution. Okay, so the solution to this problem is to think about densities. So let me explain what I mean by that. Let's take any 3 by 3 square on the board. Let's say this one here. And now what I notice is that I can only ever have 1, 2 inside this 3 by 3 square, or at most 1, 2. So I have 1, 2 here, and I know that I can't have another one. And the reason for that is if I tried to have another one in here, let's say even if I tried to make it quite far away, so in this corner, these would still be distance 2 apart. And so the distance between them is not strictly greater than 2. So I can't have a 2 there. And even if, I had them in opposing corners, the distance between them would still be at most 2. And so any two squares I choose inside a 3 by 3 square, they have distance at most 2 apart. And so therefore, I know that in any 3 by 3 square, I can only have 1, 2. A similar argument holds when you look at 4 by 4 squares. So if I imagine I'd filled in these numbers here, if I looked at this 4 by 4 square here, I could only have at most 1, 3 in there. So I've got a 3 here, and I know I can't have any more in them because all the other squares are going to be distance at most 3 apart. So 1, 2, 3, for example, for that one. So that tells me that in any 4 by 4 square, I can only have at most 1, 3. So what does this tell me about the density of 3's? And here, density, I mean kind of the proportion of 3's. So imagine I had filled in my whole infinite chessboard with these with positive integers satisfying this property. How many 3's or what would the proportion of 3's be? Well, I know for a fact that the proportion of 3's would have to be less than or equal to a 16th, because I know that in any 4 by 4 square, which obviously contains 16 cells, I can only have at most 1, 3. Therefore, the proportion of 3's, so maybe I'll put proportion of 3's, is less than or equal to 1/16. Similarly, we know for 2, the proportion of 2's in here is going to be less than or equal to 1/9. So the because you can only have 1, 2 in every 3 by 3 square. And similarly, you can't have more than 1 in any 2 by 2 square. So the proportion of 1's has to be less than 1/2 squared, which is a quarter. And similarly, the proportion of 4's has to be less than or equal to 1/25, because you can't have 2 4's in the same 5 by 5 square. And so what we notice is that if we just add up all these proportions of all the numbers, in theory, we should get 1, right? Because if we filled up the whole chessboard, the whole infinite chessboard, with these positive integers, we should get 1. But that's impossible, because if we add up these numbers here, this is 1 over 2 squared, plus 1 over 3 squared, plus 1 over 4 squared, plus so on. And this is almost a very famous series. We're just missing the 1 over 1 squared at the top. So this is minus 1 plus the sum from r equals 1 to infinity of 1 over r squared. And this, hopefully you've seen this result before, this number here is pi squared over 6, which comes from a famous problem called the Basel problem. So if you've not seen why that's pi squared over 6, I'll link a proof video I've made about that, and the proof video is actually quite interesting. It uses a probability, but anyway, I'll let you discover that if you haven't seen that already. But this thing here equals pi squared over 6, so it's minus 1 plus pi squared over 6. But you can just use your calculator. Pi squared over 6 is 1.6 something, so if I subtract 1 from that, this is only 0.6 something something something, and definitely not going to be equal to 1. And therefore, it's impossible to cover an infinite chessboard with these positive integers, because if you could, then the proportions would have to sum to 1. So the proportion of 1s in your board, plus the proportion of 2s in your board, plus the proportion of 3s in your board, and so on. It would have to sum to 1, and we've shown that it's going to sum to something that's less than or equal to minus 1 plus pi squared over 6, and therefore cannot equal 1. And that solves our problem. It is impossible to fill the chessboard in with these positive integers. So I hope you have enjoyed this problem. This was inspired by a problem I found online, and the person who solved this actually, the person who, this solution, they also talks about what happens when you change the distance. So in this distance, we're kind of allowing for diagonals, but if we change it so like the distance between this one and this one, it's not 2, but it's 1, 2, 3, so we can only go horizontally or vertically, then you get a different answer. It turns out it is possible, but that's much more difficult to prove. But anyway, I hope you have enjoyed this video. I'll let you explore this problem if you're interested. As always, thank you for watching. If you do have any suggestions for videos you'd like to see, do let me know in the comments. But apart from that, thank you for watching. I'll catch you in the next one. Have a great day.